Hello. This is the third chapter of eco320 economic statistics. So we are entering another area of statistics. So remember, in the first two chapters, in chapter one, we learned the definition of probability, and in chapter two, we learned conditional probabilities. So in those two chapters were about probability. And this chapter and the next one are about averages. So averages that you use every day, and the average you know. And of course, we are going a little deeper than the simple average, but basically we are going to learn the average, the more rigorous formal definition of average, and its alternatives and its variations. So the main theme of this chapter and the next one is the average. So these two, probability and average, are two most important building blocks in statistics at any level. From the introductory statistics to the up-to-date most advanced statistical theories. Basically, they all theory are based on is based on these two main ways to describe and formulate the randomness. To compare them, probabilities are more theoretically and mathematically important, more theoretically complete. However, as you know, average is more practical, more useful, and more commonly used in your daily life. So, still, both are very important, but maybe learning about the average can be more efficient, more useful, and efficient way to summarize the data. So you will see why. Let me start. So let me start with the relevant textbook chapters. So in case you want further readings, uh, find them. And so let me start with a simple motivating question. So suppose you have data on used car market. So you have market data for used cars, and for each car or each transaction, you observe the following outcomes. First, you observe the price or listed price, and second, you observe the make and model, and the year, the model year, and model year means, like, say, when the car's model was produced, like 21 Camry or 2020 Camry. Even though they look the same, the model year changes. There is slight change every year. And mileage on the car, and the number of major repairs a used car had. So then let me ask you a question. You can imagine what kind of data it is. It's quite straightforward what I'm talking about. I am like, the question is, there is a variable among these five. There is one variable for which we cannot calculate the average. What is that? Think about that. You would like to calculate the average, and you have the data, but you cannot calculate the average for one. What is that? Let me turn the page. The answer is number B. Basically, the key idea is that to calculate the average, the variable must be a number. The variable must be a number, and if you go back, so price is a number, and make and model, skip that. Price is a number, year is a number, like 2020, 2019, 90, and mileage is also a number, and number of major repairs is also a number. So all the other four variables are numerical variables, obviously numerical variables. But B, make and model, like Toyota Camry. I have Toyota Camry, and it's not a number. So to to calculate the average, you should be able to take the average of, say, Toyota and Ford, say Ford and GM and like BMW. What is the average of them? there is no average of something that's not a number, right? So to calculate the average, basically it has to be a number. So average is not defined if a variable is not a number. That's that's one of the reasons why probability is more mathematically complete. Sometimes average is not defined. So, but still it's pretty useful if the variable is a number, right? So, of course, to study the average, we have to assume that all the variables are, so from now on the variables will be numerical. We will assume that uh, the variables are numerical. Otherwise, there is no average. So we will consider numerical variables only. And similar property. So there are other like measures, statistical measures that require the variable to be a number. For example, average or maximum or minimum. To find the maximum or minimum of something, you should be able to compare them, which is greater and which is smaller. To do that, the variable must be a number. And variance and standard deviation, I believe you have heard about them. And median and percentiles, which we'll learn next week. So anyhow, everything you learn in this chapter is based on numerical variables. They are defined only for numerical variables, right? Okay, so let me start with then. So let me start with the term random variable. So random variable is a numerical description of outcomes from an experiment. So far, in the first two chapters, we denoted events. The main focus of our analysis is on event. We learned what is the intersection of two events, or union of the events, or what's the complement, and what's the condition, what is the main event, something like that. So everything is focused on events, and they were denoted by an alphabet. But from now on, we will make the outcomes numbers. We have to turn the outcomes into numbers. So in most cases, it's obvious. For example, think about coin toss. In the first chapter, I used coin toss example, and the coin toss example had head and tail. So I denoted them head, H and T, H for head, T for tail. But to calculate the average, or something like numerical, to make it numerical, we are going to rewrite them as 0 and 1. Say 1 is head, 0 is tail, right? So when you just rename the outcome as using numbers, that's what you are doing, and then we call this a random variable. And if you think about dice, it's easier. So there is a natural uh, way to express the outcome as a number in the case of dice rolling. And so, for example, YouTube video view count. How many views it had? It's also automatic number. Automatically, it's a number, non-negative numbers, non-negative integers. Or if you think about stock return, it can be negative, can be positive, and can be a fraction. So any rational numbers would be the possible outcomes for stock return. So in most cases, the outcome can be expressed as a number, and we are going to call that a random variable. So more mathematically speaking, random variable is a function from the outcome to a number. That's random variable. So anyhow, random variable is a numerical description of the outcomes. Okay, so this is the basis of what we are going to do, because we will assume that the variables are numbers. So we are going to define notation based on this setup. So usually we are going to denote the random variables as x, y, or z, right, as a capital letter. And probability, we are going to denote probability in this way. Say, for example, probability of random variable x equals to lowercase x, or probability capital letter y smaller than or equal to lowercase y. So when I say, so for example, think about this. What is the probability that the outcome on a die equals 6, for example? Probability that the number on the die equals 6. In this case, so probability corresponds to PR notation, and that the number on the dice equals 6 will be inside the parenthesis, and the number on the dice will be denoted by capital letter X, and 6 is replaced by lowercase x. Then the major difference between uppercase and lowercase is that the uppercase stands for, like, it's usually for a random variable, which is a general random object. It is not realized. So when I say number on a dice, it's random, but it is not realized. It can be 1 or 2 or 3, like 6 or whatever. So when I say a number on a dice, it's random. It's a random variable. But when I say 6, that equals 6, then 6 is not random. 6 is just a fixed number. It does not change. You are interested only in that. So the usage of uppercase and lowercase letters are different. And I will try my best to stick to these two principles. So using uppercase for random object and lowercase for fixed number, just one of the possible values. So it's keep that in mind. Later, the distinction becomes more important because you have to tell what is random and what's not to calculate the probability. And whenever obvious, I may shorten probability that random variable x equals lowercase x will be, simply I will drop the random variable, because when it's obvious, when in the context when there is only one variable, then I don't need to denote it. So then I will rewrite this way. Also, when the experiment is repeated, then we have to denote uh, multiple outcomes from repeated experiments. In that case, I'm going to use subscript. And usually the number of repetitions will be denoted as n, sample size, right? So x1 is the outcome from the first experiment, x2 is the outcome from the second experiment, right? If you can think about survey, x1 is the answer from the first respondent, x2 is the answer from the second respondent. In that way, you survey up to n number of individuals, right? This is the basic notation. And yeah, I prepared coloring. I forgot that. So think like look at the structure. Whenever you define a probability, you have to have a random variable, and you have to compare that to a fixed, specific number. So okay, it's been 14 minutes. So I'm going to stop the video right here, and I will give you another example to see why on average the average is important. So see you later.